So in chapter 10, we are talking about plane figures. And then we will talk about figures in space, three-dimensional figures. So in the review sheet that I posted, you had several things that you were supposed to look over that you should recall from geometry. And one of those was the definition, or actually the description of a point, line, and a plane. And we can think of a curve as a line. It doesn't matter whether or not it arcs or anything. But some path of points that we can trace with a single continuous motion. Oftentimes in elementary school, we kind of distinguish between a curve and an arc and a straight line or a line segment. But a line segment is just still a curve because it can be drawn with one singular continuous motion. So we have three types of curves. One is simple, like A here, where you start at one point, end at another, but the curve at no point intersects itself. So that's a simple curve. A simple closed curve only intersects itself at one point, and that's the same point where it starts is the point where it ends. So I start here, trace the curve, end here. But there's no other point where the curve intersects itself. So this is a simple closed curve. C is closed because I can start at one of the points, make a continuous motion to trace through all the points, and it ends where it started, but it also happens to intersect itself at another point. Okay, so we say this curve is closed, but it's not simple. Now, if I take a simple closed curve, so that's all the points that are on the curve, and then combine those points or union them with the points inside, what I get is a plane region. And we can classify plane regions as concave or convex. Concave is usually easy to remember because you can think of something caving in on itself, and that actually does come from the Latin, which means hollow. So there's a point at which it's hollow. However, we want to just not define it by saying, oh, it's hollow. So we want to be more precise. So a figure is going to be concave if I can find 2 points. Okay, I can find 2 points, and this, when I connect the line segment between them, I'm going outside of the figure. The same thing here. If you can do that, then your planar region is concave, and it looks caved in. If a figure is not concave, we call it convex. And here, it doesn't matter any 2 points you pick that are within the region. The line segment that contains them is also going to be in the region. Now, a circle is probably the most familiar simple closed curve we have. So, the curve that's simple, that starts and ends at the same point, the points on that curve or on the circle are what defines the circle, not the region inside. Okay? And a circle has a special point that's a center. And a circle is defined as the set of points that are equidistant, or all are the radius, will be the length of all the line segments from the center to any point on the line. We have a couple other line segments that are special to a circle besides the radius, which is any segment between the center and the circle itself. One of those is the diameter. So its endpoints are on the circle and it has to pass through the center. Then we have a chord. Its endpoints are also on the circle, but it does not pass through the center. Now, a chord can pass through the center, but if it does, we call it a diameter. And then we have a special line associated with circles. In fact, not just one special line. There's an infinite number of these lines that we can draw that touch the circle at just one point. So I could draw that. And each of these are called tangents. So any of these that just touch, whoops, sorry, I hit two things at once, touch the circle at just one point is called a tangent. You can think of it like if you've ever swung a set of keys around and then they fell off or let go, or you let go. This line at which they travel off is the tangent line. So when we say someone goes off on a tangent, that's exactly where we get that from. So here again is the definitions for a diameter and a tangent. And then of course the distance around the circle is called the circumference. If I take this closed curve and union it with all the points in between, or inside the region I should say, then I get what we call a disk. So polygons, and I looked up polygon, and it actually, I think gon meant knees, so it has bends in it, like you bend your knees. But it's a simple closed curve that is the union of line segments. Okay, so a circle would not be a polygon because it doesn't have line segments. Line segments have to be straight. So if I take a simple closed curve whose sides are line segments, that's the polygon, and if I union it with the points inside, all that together is called the polygonal region. One way to classify polygons is according to the number of line segments that make up the sides. And you should be familiar with these. Triangle, of course the tri means 3. Quadrilateral, quad is what we use for the prefix of 4 in geometry. Penta, 5, hexa, 6, and so forth. And you will need to know these. Any other number, like a 15-sided polygon, we would just call that a 15-gon. These are special, and then there's one more we called a icosagon. Besides those, any others we call just an n-gon. So the line segments we call sides, and the endpoints of each of the line segments are called vertices. Now if I have a polygon, and this isn't going to be really pretty because I'm drawing it by hand, but imagine this is a rectangle. If I look at side AB, so that line segment, and line segment BC, they share an endpoint in common. B is in common to both of them. So we call these adjacent sides because they share a common vertex. Whereas AD and BC would not be adjacent. If I look at the vertices A, B, they share a line segment, AB. So they have a common side. So they are called adjacent vertices. So A and B are adjacent to each other, whereas A and C would not be adjacent. So A and C are non-adjacent. And A and B are adjacent. So here I've got, and I'm going to label the vertices here of this pentagon. It's a pentagon because it has 5 sides. And if I look at A, now B and E are both adjacent to A. But if I draw the line segment that connects A to the other vertices that it's not adjacent to, what I create is a diagonal. Okay, so it depends, the diagonal itself depends on which vertex you're looking at. So here we have the diagonals that have B as an endpoint, and then you can see the diagonals where we have C as an endpoint, D as an endpoint, and E as an endpoint. So going back to the triangles, which we kind of already talked about a little bit, we can take these 3-sided figures and classify them according to their sides or the angles which they contain. So in a acute triangle, all the 3 angles are acute. They're less than 90 degrees. In a right triangle, one of the angles is 90 degrees. In an equilateral triangle, we have all 3 sides are congruent, equal length, which also implies that all 3 angles have to be of equal size. Okay. So you can say it's equilateral, or you could say it's equiangular, but we don't usually say that. The scalene triangle, okay, so the relationship between its sides is that all 3 sides have some different length. Isosceles, I'm going to have 2 sides that have equal length, 2 sides that are congruent, which also means that it's going to have 2 angles that are congruent. Now notice this definition says at least 2 sides of equal length. So an equilateral triangle is a special type of isosceles triangle. And then we have an obtuse triangle because one of its angles is obtuse, which is greater than 90, less than 180. And we also can classify different quadrilaterals. Remember, quadrilateral means 4 sides. By looking at their side lengths and angles. A trapezoid has a pair of sides that are parallel. If I take the trapezoid and give it congruent base angles, or make these sides congruent, then I have an isosceles trapezoid. The non-parallel sides have equal length, they're congruent. In a rhombus, opposite sides are parallel and all sides are equal length. So opposite sides are parallel, but all sides are congruent. Then we have a parallelogram. Okay, both pairs of opposite sides are parallel, so that pair is parallel to each other, and these two are parallel to each other. And then we have equal lengths on the opposite sides. So if we take a parallelogram and then make it so that the angles are all the same, 360 degrees, we have a rectangle. And then if we make all the sides congruent, so we have all the same conditions except now the adjacent sides are also congruent, we have a square. One other that I do not have a picture on here of is a kite. And all of you should know I know you know what a kite looks like. And this isn't a very good drawing, but the adjacent sides of a kite, there are two sets of adjacent sides that are parallel to each other. That's what makes a kite. It has two pairs of congruent, in this case not opposite, but adjacent sides. And I just wanted to kind of just give you an idea. You don't have to memorize these or anything. But if you look at the Common Core State Standards for Geometry, which you all should really be getting used to, these are starting kindergarten, okay? And look at all the different geometry expectations and standards we have just in the grades that you might be teaching. So it's very important to make sure we understand this.